As Bastien just said, I'll be talking about the Sahel and the impact of climate change over the Sahel. So basically the Sahel is here, so it's located here in West Africa. What you can see on this map is you have the continent with the black borders and black lines, and we have the precipitation in colors in summer. So basically the Sahel is a transition area between this part, which is very humid, and the Saharan desert, which is very dry. That's this transition period. And there is this seasonality of the precipitation over this Sahel. So if we do an average of the precipitation roughly over this box, but looking at how precipitation is changing through time from January to December, I should use that, from January to December and by degree of latitude, what we can see is that the precipitation are shifting north from January to the summer. So you have the northward shift of the monsoon, of the ITCZ overland. Then we get monsoon seasons here. Like this Sahel, what you can see is like we are more between 10 to 12 degrees, 10 to 20 degrees north in latitude. So we have the monsoon here over the Sahel in summer, and then we have the southward shift of the monsoon. And this seasonality, this shift in the precipitation over Africa is basically following some gradient in temperature and the maximum of temperature over the Saharan desert, over land. That's what we have with the colors. So we have the seasonal cycle of the monsoon. It's very important in summer. It's breaking most of the precipitation, and that's very important for the agriculture. But we also have a strong variability of the precipitation. So what we can see here is the precipitation average across the Sahel. And what we have, mostly the western part of the Sahel, and what we have is that we have a strong variability from a year to another. And mostly something that's relatively clear here is that we have periods of several years, like 20 years, in which we had anomalously high precipitation, and periods for which we have more like a decrease in precipitation. So you can see this decreasing trend in precipitation from the 1950s to the 1980s, 70s, 80s, and early 90s, which were actually a drought that occurred over West Africa. It was very important for the countries over West Africa. It had a lot of consequences. So we try to understand a bit the causes of this drought and what's leading to changes in the variability, like climate variability over West Africa. But what I'll be focusing here is more about what will happen in the future. So what we can see here is that from the 1990s to nowadays, we have a kind of a recovery of the precipitation. We have a positive trend, so it's raining a bit more over the Sahel. And what we wonder is if we will have in the future a continuity in this recovery. Will we get more precipitation, or are we going to a new drought or to less precipitation? Because of course all of that has effects on agriculture, human health, and there's a lot of consequences. So of course, to look at what would happen in the future, what we need is to look at different scenarios, to look at climate models, because we don't know what will happen, basically, so we have different hypotheses. What I've shown you here is basically the change in precipitation for the end of the 21st century. So it's relative to the end of a historical period which is 1960, 1999, and that's in summer. So we have a different bar for each model. So basically we have a model here, GFDL, which is projecting into less precipitation at the end of the 21st century, and some models which are showing more precipitation at the end of the century. So if we do a multi-model mean, so the average across all models, we have this red bar on the right here. So we can see that in average we have a small, moderate increase in precipitation at the end of the 21st century, but that there is a very strong divergence between models. So there is a large uncertainty. We have the intermodal spread here with those two lines. So there is a large uncertainty about what will happen in the future, and basically we don't really know what will happen in the future because it's really model dependent. So we try to understand that a bit better, so looking at the sources of uncertainty. So first what I've done is to compare what we get from two ensemble of simulations, of two generations of models. On the left we have the change in precipitation we get for the end of the 21st century with the semi-5 models. What we get is an increase in precipitation over the center of the Sahel here, this box, a decrease over the western part of the Sahel. That's MIP 5. So if we look at the new generation of models, MIP 6, that's what we have on the right. We have basically the same ID. It's a bit stronger in terms of magnitude here, but we have the same ID with a relatively similar pattern, a dipole of precipitation across the Sahel. And if we look at the ensemble spread, so that's the dispersion, divergence between models, basically. That's what we have here with the blue colors. What we can see is that basically the spread, so the differences between models, between the different simulations, is sometimes stronger than the change we have in average of all simulations. So basically it's very hard to know what would happen in the future because of those uncertainty. It was the case for the SIM5, for the new SIM6 models. We have very strong similarities with a lot of uncertainty. So what I've done is to try to understand a bit better, and to do that, I look at the precipitation. Basically, I try to decompose the different sources of precipitation changes. So we've used a first assumption, which were from some papers, like this one of Held and Soden. It was making an assumption, basically, that we can approximate the change of the precipitation by the change in the circulation of the change in specific humidity. And what we've done is just to say that P, which is the precipitation, would be equal at Q is the near surface specific humidity, so that's the humidity you have, and star, which is here, it's more a metric to estimate the strength of the atmospheric circulation. So it's a proxy for the conflictive matrix. That's the fact that you have the humidity, that you are getting this humidity into more altitude and you're getting precipitation. So we'll see it here as a dynamic term, while Q is more a thermodynamic term. So that's the fact that you have a warmer climate, so more moisture in the air, more humidity, and you can get more precipitation. So it's that's an assumption. So it has been shown to be a good assumption in some paper, like the work of Rob Chadwick in Met Office. And what we can do then is to decompose those changes in precipitation. So we have delta P. That basically, if we just look at the change of precipitation, we have delta P. That's a change. So basically, that will be here. So the precipitation we have at the end of the 21st century minus what we have over a common historical period, which is still 1960, 1999. And what we have is that I can look at what is due basically to the change of the specific humidity alone. That will be the thermodynamic term. So the fact that we have a warmer climate, more moisture, and then more precipitation because we have more moisture. Get more convergence, moisture flux convergence. We have what we get when we have a change only of the circulation. So it's just a dynamic term for the same amount of humidity. If we have a strengthening of the wind, we will still get more moisture, so it will come to the Sahel, and we will get more precipitation. And we have a cross term, which is basically what is due to both, in the meantime, changes in precipitation and moisture. Then we went also a little bit further than that, knowing that this dynamic term, we can decompose it into two other terms, the weak term and the shift term. So that's other assumptions. The weak term is associated with basically the change of the tropical mean circulation. And the idea is that when you get a warmer climate, you have an increase of the SSTs, so you have also an increase of the evaporation and of the temperature of the troposphere, the top of the troposphere, and you get a stabilization of the atmospheric column. So because you have a stabilization of the atmospheric columns over the tropics, then you get a weakening of the atmospheric circulation over the tropics, and you're supposed to get less precipitation. So on the Chadwick's papers, what they've shown is that this term is proportional to the tropical mean circulation. So basically, it's at this dynamic term, you do the average across the tropic. It's inversely proportional. You have the minus term. So we can look basically of what's associated with the change of the large-scale circulation over the tropics. And if we just do the difference, we just remove it, subtract it from our change of the circulation, we have what is the shift. So what it's not associated with a change of the tropical mean circulation, which is a shift, which is more like if we have a southward, northward shift or some position of the atmospheric circulation. Okay, so what we can see here is basically what I've shown here on the top is the spread, the ensemble spread. So it's one standard deviation computed across all models for each of those terms. For the change in precipitation we have for the end of the 21st century, always in summer, which is July, August, September. What we have here is the thermodynamic term on the left, So we can see that we have already a spread which is quite high, because we can get up to like 0.6 to 0.8 millimeters per day on some of the grade point. But when we look at the spread we have with the dynamic term, clearly we have a much higher spread for the dynamic term. So much of the uncertainty, but we show here that much of the uncertainty are mostly coming from the dynamic of the circulation. The models disagree on how the atmospheric circulation will change in the future. The cross term is a bit weaker, so we have less uncertainty associated with that. And what we have on the bottom is basically the precipitation change, but average over two boxes that I've shown before. So it was, sorry, those two boxes for the western and central Sahel. So basically a box for where we have the decrease in precipitation over the western Sahel, which is a large part of Senegal and West Mali, and a box in where we have the increase in precipitation over the center of the Sahel. Okay, so if we do that, here we have the thermodynamic term. We have a different circle for each of the CM5 model, so the change in precipitation with a thermodynamical term. We clearly have already a large spread. We have the same thing for the M6 with the squares. We have the ensemble mean with the cross and the spread with a gray shading. For the west of the Sahel on the left and the center of the Sahel on the right. So if we look at those results for the thermodynamic, dynamic, and cross term, clearly we can see that we have more dispersion for the dynamic term. And another thing is that for the thermodynamic term, they all agree that we will get more precipitation because it's getting warmer, so we get more precipitation. While for the dynamic term, there are much more divergence. And we can see, so they agree more or less for the western part of the Sahel that all models are estimating a decrease in precipitation due to the change of the atmospheric circulation. But over the center of the Sahel, they a bit disagree on the thing of the change, and there is a large spread across models. So there is really a large divergence here. And what we've shown, basically what we suggested is that this uncertainty is mostly due to this dynamic term. So this dynamic term, we have decomposed it into the two different terms. The weakening of the atmospheric circulation. So we get a weakening of the atmospheric circulation in the future because of the change in the temperature and of the vertical gradient in temperature. So we get less precipitation in the future, and that's the case for all models of the same 5 and same 6 ensemble. With a spread which is not so high if you compare to the shift of the circulation. And in the shift of the circulation, we really have large differences between models and simulations, in which we have some things that we've seen a little bit before, that basically we have a kind of decrease in precipitation on average across the western part of the Sahel and more precipitation over the center of the Sahel, but we have really a very strong spread there. So that's where basically we are getting, let's say, troubles with those climate models to simulate what will happen in the future. We need to understand better how the circulation will change and how the pattern basically of the atmospheric circulation will be impacted by climate change. So that's a way to show it basically, which is that we know that the change in precipitation is due to the change of the thermodynamic term. There's the dynamic term, which is basically the shift plus the weak term. So if you sum those two, you have the dynamic term and the cross term. So if I take those differences for all models, but instead of having here for the thermodynamic term, so you do the differences for all models. So if you have 40 models, at the end you have 40 values of delta P. You do the standard deviation across those 40 values, and you get a map of standard deviation for each grade point. You do the same thing, but instead of having the thermodynamic term for each of the models, you compute the multimodal mean. So you have the same thermodynamic term for all models. And then the spread you have at the end is not coming from the thermodynamic term. So you can see that we still have this very high spread. So averaging the thermodynamic term is not removing the ensemble spread we got. If you do this for the weak term, we still have a very high spread. If we do it for the cross term, we still have, those reduces a bit of spread, ensemble spread, but we still have strong differences and uncertainty. And if you do it with a shift term, this time you've removed the main source of uncertainty, and basically you have this ensemble spread, which is much weaker. So it's just a way to show that clearly that's this shift in the circulation is very important across those models for the uncertainty. Okay, so we've shown, it was a paper that we've published in Climate Dynamics in 2020 that most of the uncertainty is due to this shift in the circulation. So in the paper, we looked a bit at some gradient in temperature and different metrics, but I will speak about that just a little bit later. What we show is that also, it's not that, so the different models, they also simulate different changes in the global mean surface air temperature, but it's not like the models which are the warmer in the future will do more precipitation than the others. It's really how the atmospheric circulation will change, and that's mostly due to the gradient of temperature, not by the global mean surface air temperature by itself. So it's a bit more complicated. So then we've done another study, which is basically to try to follow up on the first one I've shown you. And here, what I'm showing here is basically, so I've computed the change in precipitation average across the Sahel. Oops, sorry. Okay, across the Sahel. Basically, so I have the change in temperature for all the models I have here. I have the change in temperature, so in precipitation average over the Sahel for all models I have here. So the change in temperature for all models and over all grid points. And if I just do a linear regression between the change in precipitation and the change in temperature, I get this map. And basically what this map is showing is that the models which are warming more than the others over the northern hemisphere, so North Atlantic and the Euro-Mediterranean area that I've those boxes. So it's basically the North Pacific, the North Atlantic, Europe, Mediterranean Sea, and a part of Asia. Models which are warming more there, they are producing more precipitation than the others at the end of the 21st century. So there is something about the gradient in temperature between the northern and southern hemisphere, which is important. And we know that it's a gradient which is important for the monsoon. It's been shown also in some paper of Park et al. 2015 and 2016. I've selected two boxes to try to understand the drivers of uncertainty here, which are the North Atlantic and the Euro-Mediterranean area, so the green and blue boxes, because we know that there is a strong link between the changes of the temperature over the North Atlantic Ocean and the precipitation over the Sahel. So the North Atlantic Ocean is a strong source of variability. Like for the multi-decadal variability of the monsoon, it was one of the drivers of the drought over the Sahel in the 1970s, 80s. And the SST of the Mediterranean Sea is important as well for the precipitation over West Africa. There are some more and more papers on that. There is this paper of Park et al. In which he was showing basically the same kind of maps, and they've made simulations showing that yes, we have warming of the northern hemisphere, which is important for the Sahel. So what happens if we just increase the SST over the northern hemisphere? Then we get a strong increase in precipitation over the Sahel. If you do the same thing for the global mean change in temperature, changing the SSTs everywhere over the globe, they do got an increase in precipitation. It was just stronger with the northern hemisphere, and what they've shown is that the tropic and south hemisphere didn't really play much of a role on this change in precipitation. And then they decomposed what's happening when you look at the northern hemisphere. So basically you warm up the Mediterranean Sea, you get a strong increase. In North Atlantic, you get a strong increase. And you also have changes with North Pacific and Arctic, but it was basically more like the Mediterranean Sea and the North Atlantic Ocean, which are very important on those patterns for what's happening over the Sahel. So we also use those results to say, well, we have those two boxes, the North Atlantic and the Mediterranean areas, which are important, both in terms of the current variability of the climate over the Sahel, but also the future change of the precipitation over the Sahel. So then what we've done is try to recompose, basically, to try to understand how those two drivers, North Atlantic and the Euro-Mediterranean area, could impact the change in precipitation over the Sahel. So what we've done is basically to, I will start by this one, to a pattern scaling assumption. What we've done is just we will assume that we will get a pattern, P, and we will just assume it to be, to scale linearly with the change of the global mean surface air temperature, which is delta T, and that is giving you a change for a given variable that we will be looking at. And this pattern so it's a strong assumption because we don't really know if not the Sahel over the precipitation over the Sahel will change linearly to the global mean surface air temperature. So it's an assumption as well, a new one. And And what we've done is to estimate this pattern of the change in precipitation to be just dependent on what's happening over the North Atlantic Ocean and the Mediterranean Sea in terms of temperature. So I've scaled everything by the global mean surface air temperature because I've shown you before that the global mean surface air temperature is not a strong source of uncertainty. So I'm just looking at what's relative to this global mean surface air temperature. So we are not looking at the fact that some models are warming more than the others globally. It's just what's happening over the North Atlantic and the Euro-Mediterranean area. Trying to focus more on gradients of temperature. That's a linear regression. So basically, you have the different components of your linear regressions. The A will be what's happening when you don't have the effects of the two different drivers, North Atlantic and the Mediterranean. So that would be here the effects, the BX, the effects that you have when you have differences between models at simulating the change in temperature of the North Atlantic Ocean. And here what you have due to the fact that models are projecting into different warming of the Euro-Mediterranean area. Okay, that's M for each model and X for each grid point. Okay, so it's a simple, basic linear multiple regression. And when we do with that, it just you use this formula here. So P, that's this, which is basically that you just use the formula, it's delta C divided by delta T equal P, so that's what you get here. So you have the change, in our case here, that will be precipitation and temperature, I'll show both, but the change in precipitation by degree of global warming. It's a new prediction I'm doing, and what I will get here, we had different results for different models, but the only difference we will have between those different models is that they have different warming over both the North Atlantic and both the Euro-Mediterranean area. So the only difference we have in this prediction between models is that they are warming differently, the North Atlantic and the Euro-Mediterranean area. So we do our predictions. We have the change in precipitation on the x-axis we have for each of the same 6 models. We have a different number for each same 6 model. For the Western and the Central Sahel. So that's what we have in the models, that's what we have in the prediction. And what we get is that basically this statistical approach is working relatively well. We have a correlation of 0.33, so of course we don't explain all the variability. There are some errors like in the magnitude of the change, but basically we have a model which is working relatively well at explaining the spread we have across models, which then we show is strongly associated with how models are warming the North Atlantic or the Euro-Mediterranean area. Okay, so if we do this thing for each grid point, so I have a prediction for each grid point. I just do a correlation with what I have in the models for each grid point. So it's a correlation across models. And what we get is here the squared correlation. So basically what we show is that we can explain like between 60 to 70% of the uncertainty over a large part of the Sahel. So what we say is that basically we have strong uncertainty, strong differences between the models. It's due to how the atmospheric circulation is shifting in the future, and that looks to be associated also on how the North Atlantic and the Euro-Mediterranean area are warming, because the warming of those two areas have strong dynamical effect on the monsoon by shifting the atmospheric circulation, the gradient of the circulation. But we wanted to go a bit further than that and to illustrate a bit on how different changes in temperature of the North Atlantic and the Euro-Mediterranean area could impact precipitation over the Sahel. So we've done followed an approach which is called a storyline approach, which was developed actually at Reading. So what I've shown you already is that we have this linear multiple regression. So we got coefficients. We have what's due. So the AX will be the same. So that's basically what you have. So that's the change in precipitation you have without effect of the two different drivers. You have what's due to the North Atlantic, what's due to the Euro-Mediterranean area. And we will play a bit with that, but just scaling a bit those two effects of the North Atlantic and the Euro-Mediterranean temperature with a T index to get different strength. I'll go through that very quickly, but basically the idea we have is that we want to sample 80% of the distribution. So we have a quantile function to get 80% of the distribution, and I have this part of the equation which is just because ideally what I would like to have is two drivers that would be fully independent, but what I will show you just on the next slide is that those two drivers, North Atlantic and Euro-Mediterranean areas, are not fully independent of each other. So when you have a warming of the North Atlantic, you can get also warming of the Euro-Mediterranean area, it can spread a bit. So we use that part of the equation to account for the fact that there is a small covariability between those two predictors. And basically, we got something like this. So here we have the change of the North Atlantic temperature on the x-axis. So it's all scaled by the global warming. Here we get, and that's for the end of the 21st century, here we get the change of the temperature over both the Mediterranean Sea and a part of Europe and Northern Africa. So it's a Euro-Mediterranean area, scaled by global warming. We have a number for each of the different models. And what we have, since the ellipses, in which you can see that there is basically a kind of a correlation between the two, but the correlation was 0.35, so basically we have only 12% of the variance explained in common. So it's very small, so we still assume that we can use it at two relatively independent drivers. And what we've done is to use this framework I've shown you, but with the temperature as well, to look on how we could get different warmings of the North Atlantic and Euro-Mediterranean area. So we got different scenarios, 4 scenarios. We have one scenario here, A plus M plus, which is Atlantic plus, Mediterranean plus, basically warming, strong warming over both areas, which is just by taking the multimodal mean, but without effect of the drivers, plus adding basically the effect of the North Atlantic and Euro-Mediterranean area, which is scaled to sample 80% of the distribution. So we can see that with this circle, this ellipse, we can sample most of what we have in the distribution, or inside this distribution. We have M minus M minus, so it's a weaker warming over both the Atlantic and the Euro-Mediterranean area. And we have 2 cross scenarios, A plus M minus, so it's basically warming over the North Atlantic, but cooling over, weaker warming over the Mediterranean area, and weaker warming over the Atlantic, and stronger warming over the Mediterranean area, all relative to the same 6 ensemble. So now I'll show you what kind of impacts we have on precipitation by having different changes, different scenarios with different warming over both those areas. But what we can see first is that those new scenarios, each could be a step 6 model. They are within the distributions, they are not outliers. M-minus could be a bit maybe on the side of the distribution, but they are not really outliers. Like M plus is really between some models. So that's something that could really happen in the same 6 ensemble. That's a multimodal mean, so that's basically the change in precipitation at the end of the 21st century. So we have more precipitation over the center of the Sahel, less precipitation over the western part of the Sahel. You can see the red contours are the climatology. So basically, what we have over the center part of the Sahel is the northward shift of the monsoon a little bit. It's drier over the south, wetter over the north, so it's more like a bit shifting in the north and strengthening as well, and a bit of a southward shift of the western part of the Sahel. So now when we look at the A plus M plus scenario, so basically on this one you have strong warming over the North Atlantic, strong warming over the Euro-Mediterranean area, and basically that's a strong warming over the whole Northern Hemisphere. It's not just North Atlantic, but it's all coming together, and what you get is this strong increase in precipitation over a part of West Africa. You can clearly see a dipole in precipitation with less precipitation over the tropics, more precipitation over Africa. So you have a northward shift of the monsoon, northward shift of the circulation. You are getting more precipitation across the Sahel. And that's just due to the fact that you have a warmer Northern Hemisphere, which is something that is known because the monsoon is replying very well to the large-scale gradients in temperature. For the A minus M minus, so weaker warming of the Northern Hemisphere, and basically because you have a weaker warming of the Northern Hemisphere, the gradient in temperature between the Northern Hemisphere and the tropics is a bit weaker, and you get this southward shift of the monsoon. It's warming a bit more over the tropics than over the Northern Hemisphere. So you get a southward shift of the monsoon that's mostly strong here over the Atlantic Ocean. You get a drying over the western part of the Sahel. Which is interesting because in another paper that we have published 2 years ago, I think we shown that this dipole in precipitation could be decomposed into 2 responses. A strong increase in precipitation across the Sahel, which is due to the fact that we have a strong warming of Northern Hemisphere basically, and a response that we have more with changes in the ocean circulation and SST, which is basically looks like really this one. So if you sum up both responses, you are getting up to something which looks like this with a zonide right on the dipole over the Sahel. So it's another way to decompose things. And we have the two cross scenarios, A+, MS, M+, which are giving something very similar, but that's because the effect of the North Atlantic and the effect of the Euro-Mediterranean areas within this framework are very similar. So it's a bit identical. So if you remove the effect of one and add the effect of the others, you basically get something which is a bit neutral. So you are very close to the ensemble mean. So, okay, so this one is very blurry, but basically what it's showing is that we have the precipitation average across the Western Sahel on the left here at the end of the 21st century, already in summer. Responses for each of the same 6 models I was using. In terms of precipitation, the across here is a multimodal mean and you have the spread, so basically there is a strong uncertainty. So same thing for the center of the Sahel on the right, in terms of mean spread. And what I've shown here is the different scenarios. So we have those two cross scenarios which are very close to the ensemble mean, because they do, in a way, obscure like each other's. And we have the M-, M- and A+, which are a bit extreme, but not outliers really. Maybe a M- is a bit outlier of the center of the Sahel, but it could be within the distribution. And clearly we can show that we are explaining a large part of the spread we have across the simulations just by the fact that there are different warming over this part, the northern hemisphere. So we can do the same thing. We can use that actually as a method for selecting models. So let's say we want to look at something specific over the Sahel in the future. We don't want to use too much models because we won't be able to do some dynamical or downscaling of those models. Or if you want to look at the river flow or anything, you won't be maybe able to use all those models for other reasons. You might want to select models. And what we say is that basically if you take the models which are in this quadrant and models which are in this other one, what we do at least is to explain a part of the uncertainty. So you have two different trajectories. You can select less models, but you can have a view of what would happen in the future, taking into account the uncertainty you have. So that's what we've done with the precipitation, just to check if it's working well. And this time it's just using the CM6 model. It's not doing any strong assumption or any statistical models. It's just using the CM6 models. You take the models you have here, A+, M+. So, well, sorry, first, on this one, we have the change in precipitation average across the Sahel. It's by degree of global warming, from 0 to 3. So you can see that some models, those warm a bit less because you don't reach up. Let's see, that's blurry too. But basically you have all models within a black line. You have the spread at the end of the 21st century. So that's basically when you have a warming of 2.5 to 3 degrees. You have this change in precipitation over the western part of the Sahel, which has strong spread. But if you select the model which are in the A+, M+ gradient quadrant, you have the models in red. If you take the ones which are in the MS quadrant, we have the models in blue. And you can see that at the end of the century, you have two different responses, two different trajectories. So you can start to select models thinking that, well, I might take less models, but still having two trajectories that looks like what you have in CM6. It's way better than just selecting randomly some models to do something. Something is that for the western part of the Sahel, there is still an overlap between the two distributions. So I've checked that the difference was significant, but there is still an overlap. So you can get models that will do an increase in precipitation that would be a bit stronger than for the red models. There's still an overlap on this. But if you look at the center part of the Sahel, you have two distributions which are very well identified and to split very well at the end when you have a strong warming. So yeah, we think that we could use that also to look at extremes or different things for the Sahel, selecting models, and maybe it could be used to send downscale simulations, or at least to select models. I'll be a bit quick on that because it's very blurry. But basically we have the change in precipitation on the top two panels. And what we have on the bottom is a shift of the circulation. So that's what I've shown you at the beginning of the presentation. The term which is associated with the shift of the circulation. And the only thing I want to say is that basically those two things look very similar. And what we show is that we are selecting models according to how they are warming the northern hemisphere, the North Atlantic, the Euro-Mediterranean area. This has an effect on the shift of the circulation, and we can see it very well when you look at the shift of the circulation. It's basically trying to explain a bit more the mechanisms that it's through the shift of the circulation that we are getting those differences in precipitation. And it's almost over, but that's basically something I didn't talk about, which is that the Saharanite law. So in West Africa, there is a low pressure system, which is very important as well for modulating the precipitation across the Sahel. We didn't select the Saharanite law as a driver of uncertainty because we needed drivers that were relatively independent of each other. So it's not independent. So I look at the location of the heat law. It's not independent to the North Atlantic and European Mediterranean area temperature, but basically what we have is that when we do select the models, we have something consistent, which is that the heat law is shifting more northward in some models than in others. Okay, but it's still shifting northward. Even if we have less precipitation over the western part of the Sahel, we still have northward shift of the heat law, which could look paradoxical because normally when we have a northward shift of the heat law, we expect to have more precipitation everywhere. So there are still things we are working on and we are trying to explain a bit more. Okay, and basically, I did not have results yet, but basically I'm using this historian approach to extract SST anomalies, and I am applying that into a climate model. So I've done a large number of simulations now, and we are looking on how those patterns we have identified with historian's approach could explain those different changes in precipitation across the Sahel, more looking at the mechanisms rather than looking more at something very statistical. Okay, so the key results. So we have a lot of uncertainty. Yeah, so we are looking at this into much more details for the mechanisms. Yeah, we think that maybe it could be useful for the impact studies and for communicating also on what could be happening in the future. And of course, I'm not trying to say that everything is due only to the warming of the North Atlantic or the Northern Hemisphere of the Euro-Mediterranean area. There are a lot of different sources of uncertainties. They have different models, have different convection schemes, have different way to simulate the dust, have different resolution and everything. So there are a lot of sources of uncertainties. Yeah, thank you.